So that's something else that can happen. This is here. This is my my R. Let me list this as well. My center. So my A here was 0. Here my A is 2. My R was 3, radius of convergence, and my interval of convergence was -1 to 5, excluding both endpoints. Because at -1 and 5 we got divergence. Okay. Let's do another example. I'll show you another one. What if I move that factorial up to the numerator? I'll stay centered at 0. So what if I have the sum n equals 0 to infinity of n factorial x to the n? Okay. So if I do the ratio test, I look at the limit as n goes to infinity, absolute value of the n plus first term, n plus 1 factorial x to the n plus 1. Over the nth term here, I'm not going to bother splitting it because it's not a fraction to begin with. So this will be n factorial over x times x to the n. So n factors of x cancel, leaving 1 upstairs. The n plus 1 factorial again is n plus 1 times n factorial. So the n factorials cancel, leaving just an n plus 1. So I can pull out the absolute value of x. Limit as n goes to infinity of n plus 1. As n goes to infinity, what does n plus 1 go to? That goes to infinity. No matter what x is, this is equal to infinity. Unless, of course, x is 0, then we don't even get started, because that's just a 0. So this is bigger than 1, so we always get divergence except at x equals 0. Okay. So this is a place where this series only converges at its center. Okay. Remember, a power series always converges at its center. This is one that only converges there. Okay. So here for this sum, n equals 0 to infinity of n factorial x to the n, its center is 0, because it's x minus 0 to the n. In this case, we say that the radius of convergence is 0. Okay, so when they only converge at the center, your radius is 0. And here, your interval of convergence. So you could write this as an interval if you want. It's kind of silly to write 0, 0. I have to include the endpoints. That's the only end. 0, it's its own endpoint. But since it's only one point, it's probably just to write it as the singleton set containing that point. Okay. The set containing that singleton point, I should say. Okay. So these are the three things that can happen, right? You can have a 0 radius of convergence, you only converge at its center. You have an infinite radius of convergence, you converge for all x. Or you have some finite positive radius of convergence. You have an interval of convergence centered at the center. And then what happens at the endpoints, you have to do some special tests there. Okay. Let's take another look at this case where some different things can happen at the endpoints. I want to look at trying to remember what I did here. Yeah, let's take a look at x plus 2 to the n over n. N equals 0 to infinity. Okay. So again, now we're centered at a equal to -2, right? Since it's x minus a -2. So I wanted to show you one where we're centered at a negative value. Let's try the ratio test. So we look at the limit as n goes to infinity, absolute value of x plus 2 to the n plus 1 over n plus 1. That's the n plus first term. Let's do 1 over the nth term, n over x plus 2 to the n. So the n factors of x plus 2 cancel, leaving 1 up top. I can't cancel that n with the n plus 1, right? They're not factors, but I'm going to leave that. It's always positive, so I can pull it outside the absolute value. Then the absolute value of x plus 2 has nothing to do with n. It can come out of the limit. So I'll write this as absolute value of x plus 2 times the limit as n goes to infinity of n over n plus 1. I can drop the absolute value here. As n goes to infinity, what happens to n over n plus 1? Well, if you remember your horizontal asymptotes, right, this is a quotient of polynomials of the same degree as n goes to, like x over x plus 1. As n goes to infinity, that would go to the ratio of the coefficients, which would be 1 over 1. Right? So this is like a horizontal asymptote. That limit's going to be 1. So we just get absolute value of x plus 2 times 1. Okay. So the ratio test tells me that this series will converge when that limit is less than 1. It will diverge when that limit's bigger than 1. So here my radius of convergence is 1. So my r is equal to 1. Okay. So I'm centered at -2. Let's think about the interval of convergence. I'm centered at -2. I have a radius of 1. If I go 1 away from 2 on either side, I get -1 and -3. Right? So I know when for x is between -3 and -1, this series converges. I have to check -3 and -1 individually, though. So let's try that. So let me go ahead and get rid of the ratio test here. Let's check at x equal -3. We have the sum n equals 0 to infinity, -3 plus 2 to the n over n. But -3 plus 2 is -1. So that's -1 to the n over n. Anyone recognize that series? That's the alternating harmonic series. Right? So this is the guy that converges, but it converges conditionally. Right? Doesn't converge absolutely. So this series, we get convergence at -3. I'm going to put a solid dot there to mean we get convergence. Let's try at x equal -1. We have the sum n equals 0 to infinity, -1 plus 2 to the n over n. -1 plus 2 is -1, so this is the sum n equals 0 to infinity, -1 to the n over n, or sorry, -1 plus 2 is +1. +1 to the n. But +1 to the n is just 1, so this is just the sum of 1 over n. But that's the harmonic series, right? This is alternating harmonic, this is harmonic. The harmonic series diverges. So here we get divergence at -1. I'll put an open circle there. Okay. So from -3 to -1, we get convergence including -3, but excluding -1. So I would say my interval of convergence is equal to include -3 with a square bracket, go to -1, exclude it with a round bracket. Okay? That makes sense? You can always rewind it if you missed anything. Okay? I'm not sure how much memory I'm using up, but one last thing and then I'll pause and then start another video. I did want to show you another way to attack this. Another way to think of that function. Yeah, let me get rid of this. This series, rather than using the ratio test on this guy, is notice my terms. So let me write this out again. Sum n equals 0 to infinity, x minus 2 to the n over 3 to the n. My first term is 1, everything to the 0. My next term is x minus 2 over 3. Right? My next term is x minus 2 squared over 3 squared. Okay. Or I could write that the next term would be the quantity x minus 2 over 3 cubed, everybody cubed, etc. So in fact, this is a geometric series. Geometric, with my first term, a0 being 1, and my ratio, little r, not to confuse it with the capital R interval radius of convergence, my ratio of terms equal to x minus 2 over 3. We know that geometric series converge when the absolute value of r is less than 1 and diverge otherwise, right? So right there we get convergence for absolute value of x minus 2 over 3 less than 1, and we get divergence for absolute value of x minus 2 over 3 greater than or equal to 1. Okay. Which gives me, multiply through by the 3, I get my center at 2, my radius at 3. I automatically get divergence at the endpoints. I don't have to test again. Okay. But the nice thing about geometric series is we know what they when they converge, we know what they converge to. Okay. This actually converges to a0 over 1 minus r. Right? So for this series, that would be 1 over 1 minus x minus 2 over 3, that's a mess. X minus 2 over 3. Okay. 1 over 1 minus r. If I multiply top and bottom by 3 to clear the complex fraction, I get 3 over 3 minus x minus 2. But that's 3 minus x plus 2, that would be 5 minus x. So I get 3 over 5 minus x. That tells me what function this is. This function is, this is the function 3 over 5 minus x. Okay. 1, I'm in the interval minus 1 to 5. I could write this function as this infinitely long polynomial. Okay. So in the next section, we'll see what advantage does that give us. We'll look at differentiating and integrating and what are the new functions we can come up with. Okay? Be right back.